Hi to everyone and welcome to this Roman manufacturing webinar. Right now, I'd like to introduce today's presenters. Presenting today is Don DeCordy. Don has a 38-plus year career in the resistance welding industry. He's responsible for overseeing Roman's automotive and industrial resistance welding products. Now, at Roman, he has led positions in sales, applications, product development, and COO of one of Roman's divisions. Prior to joining Roman, he held technical, product development, and sales management positions with various resistance welding companies. Don is a lifetime member of the American Welding Society, a lifetime counselor of the AWS, and currently chairman of the Education Committee of the Resistance Welding Manufacturing Alliance, along with a recipient of the American Welding Society's National Meritorious Award. He is a graduate of the Industrial Electronics program of RETS Electronic Schools in Detroit, Michigan. Now, also joining us today during the live question and answer session to help Don answer some questions is Donnie Christ. Donnie is responsible for providing support to Roman's automotive clients. Prior to joining Roman, he spent 13 years providing welding consulting services and program launch support at Ford, Chrysler, FCA, and Tier 1 suppliers. He holds a bachelor's degree in welding engineering technology from Ferris State University. He's also a member of the executive committee of the American Welding Society, Detroit chapter. Gentlemen, welcome to today's event. And with that, I'll pass things along to Don DeCordy to get us started. So Don, go right ahead.
Welcome everyone and thanks for joining us regarding this presentation on the features and benefits of new fast rise time MFDC welding technology. Question: what is fast rise time? When we refer to fast rise time, we're talking about the period of time it takes for weld current to rise from 0 amperage to the target current, and how fast it takes to get there. So how fast is fast? You can see here from the chart that when we refer to a MFDC high current pulse, this pulse is taking place between 3 and 20 milliseconds. This is very different than the conventional welding times that are 60 to 200 milliseconds long. So why is fast rise time so important? The variance in projection weld nuts and studs, along with specialized steels such as hot stamped or press hardened metals, have proven difficult to weld with conventional methods and equipment. Some aluminum welding applications have shown best results also with fast rise time secondary currents. Using these fast rise times, the equipment has proven more stable and consistent welding results. So what variables influence rise time? You can see here by the chart, number 1, secondary impedance. This is the impedance of the resistance welding machine, including the transformer, weld toolings, shunts, conductors, etc. Another factor is secondary voltage. An increase in secondary voltage drives faster rise rates. However, due to the turns ratio, change for higher voltages will also increase primary demand. And third, weld control capacity and how the weld control reacts. Weld control software can play an important role in rise time. Controls at times have governors in place to control accuracy or protect hardware. If so, this will tend to slow down the rise time. All three of these factors must be considered when designing a machine for fast rise time. So how is fast rise time achieved? Until recently, the most common process to achieve fast rise time is what's known as capacitive discharge welding, or in short, CD welding. Now there is a more advanced product available which can deliver the same results while providing additional benefits, Roman's FRT-MFDC technology, or fast rise time technology. Both capacitive discharge welding and Roman FRT-MFDC technology have some major advantages over the other standard resistance welding processes. Some of these include weld nugget formation, which takes place during the first few milliseconds of the welding process. This same processes allow extremely fast energy release with large peak currents. A greater percentage of the energy goes into the weld formation and less into the surrounding material because the heat is rising so fast. The heat-affected zone, where the properties of the metal have been changed by rapid heating and cooling, are also localized into a much smaller area around the weld. The quick discharge rate allows electrically and thermally conductive materials such as copper, aluminum, and other high conductive materials to also be welded. Both CDW and the FRT-MFDC process can deliver repeatable welds even during line voltage fluctuations. So what's the difference between the two technologies? There can be some significant differences. The Roman FRT technology does not use capacitors to store energy. This allows the operator to program custom wave shapes using the MFDC controller. The CDW process does not allow the customization of a wave shape. So what's so important about customizing a wave shape? You can see in the chart below, in red, a customized wave shape made from the FRT-MFDC technology. The short spike at the beginning of that wave shape allowed the user to puncture through a coating, then drop the current down to what was required to actually weld the part, and then taper it down again at the end. Once again, very different than the blue outline of the CDW waveform, which is not customizable. This can make a big difference in the quality of the weld and the consistency of the process. So what are some other significant differences? In many cases, the FRT technology can actually achieve faster rise times compared to CDW. The FRT technology allows welds to be made every half second. CDW technology generally requires 1 or 2 seconds in between welds to allow for the charging of the capacitors. The capacitors also can have a limited life based on the number of charges and discharges. This is not the case with the FRT-MFDC technology. The graph below shows a comparison on the same welding machine of the FRT technology and its rise time compared to the CDW technology and its rise time. You can see in this example, the FRT technology reaches peak current faster than the CDW. In some cases, this can help with making good welds in your process. So let's take a look at a Roman CDW transformer compared to a Roman FRT-MFDC power supply. You can see on the left this transformer, a typical CD transformer, is quite large. This one here shown is 550 millimeters high, 370 wide, and about 685 millimeters long. And it's substantially large and heavy. You can see on the right a Roman FRT-MFDC power supply. It's substantially smaller. This unit is 170 millimeters high, 150 millimeters wide, and about 480 millimeters long. It is also substantially lighter than the large CDW transformer. So what does this mean? Recently, we were asked by a customer to do a comparison of the CDW versus the Roman FRT-MFDC fast rise time technology. The following example is from that actual customer production application and what we did to compare the two technologies. The initial customer solution was using the CDW process to solve weld issues on hot stamped press hardened steel. The layout below shows the customer application using the CDW technology. Initially, the customer solution was using 3 CD machines to solve this issue on the hot stamp press hardened steel. You can see machine 1, 2, and 3 in red, 2 operators in green, and the part flow in blue from left to right, where the 2 operators took the parts and sequenced them through all 3 machines to add M6 nuts, M10 nuts, and in the end 1 M8 nut. This system used 3 dedicated CD capacitive discharge welders, 2 operators, and the combination of workflow, they were making approximately 2 parts per minute. After carefully studying the existing customer's CD welding process, a new solution was created using the Roman FRT technology. The diagram below shows what was done in order to achieve a new result. On the left-hand side, you see a single controller with an MFDC welding control and 4 switching SCRs. Each one of those 4 SCRs is connected in one machine to 4 FRT transformers. There are 4 welding guns, one connected to each transformer, that will make the 4 nut welds at one time. You can see the sequence of operation on the right behind that operator in green. The part is loaded. All 4 guns come in at once. The SCR switches sequence the 4 transformers one after the other so that each transformer has its own welding schedule. All welds are done in less than 1 second. All 4 guns are opened. Operator unloads the part and repeats the process. Below gives you an idea of the differences. This system used 1 weld controller, 1 machine with 4 Roman FRT-MFDC transformers, a single operator, and you can see by yielding 10 parts per minute, they have 5 times the output of the machine with a single operator shown in green. This is a substantial increase in productivity compared to the existing CD technology that the customer had. This is one way, because of the size of the FRT transformer and being able to put several of them inside of a single automated machine, that this technology has a huge benefit when compared to individual CDW machines. So to summarize the Roman FRT-MFDC features and benefits, you can see by the previous example that smaller transformers compared to the CDW machines require less space and allow us to use multiple transformers in a single machine. The FRT technology also uses standard MFDC welding controls, where the CDW is very control brand sensitive. Unlike CDW, the Roman FRT-MFDC can also provide custom current wave shapes. We showed earlier where a single pulse right at the beginning of a wave shape can be helpful to puncture through coatings and differentiations in metal. Also, you can see increased productivity by using the FRT-MFDC technology. The same example previously showed lower operating and labor force costs using the multiple FRT units in a custom tool versus single standalone CDW type equipment. The FRT has proven to be less expensive in many applications compared to the CDW process. And another thing that's important to point out is that you can reuse and repurpose the FRT technology where it's much harder to do a specific CDW machine, which lacks this flexibility in reuse or repurposing. One thing that I would like to point out before the end of the presentation: we believe at Roman that both the CDW process and the FRT-MFDC process will both provide fast rise time and good solutions for the materials that require it. The purpose of this presentation was to show you where the FRT technology can be used to augment the customer's requirements and where it has some advantages even compared to the CDW process. In some areas, there are also advantages that the CDW process offers. Thank you very much for joining us for this presentation, and we'll be open for questions.
Thank you, Don, for that presentation. My name is Scott Rittenauer. I am Roman Manufacturing's Corporate Marketing Manager, and I will be moderating the live Q&A today for the webinar. I am joined with Don DeCordy, VP of Resistance Welding Products, and Donnie Christ, Accounts Manager and Welding Engineer. Don and Donnie will be answering any questions you may have, so you have the option at the bottom to type in your questions. Please do so at this time. Now we'd like to open up the Q&A and get some questions from the audience. Let me first begin with the first question. Here's one. Don, can you please answer this? What weld controller was used for this customer application? And it's a two-part. What weld controller have the ability to make custom waveforms for, I can't read the whole thing here. For current control.
Good afternoon. First of all, we have a couple other questions here related to the same topic. Another question's just come in that says, what other weld controller brands can use FRT? This specific presentation was made, and that specific solution that you saw was done with a WTC controller. We have done tests with Entron. We have done tests with Harms Wendy, as well as with Amada Miyachi controllers. All of them have provided exceptionally fast rise times, so the specific transformer is not sensitive to a specific controller.
Okay, thanks, Don. Donnie, we've got one here. What is the cost of this unit compared to existing technology?
The cost of the FRT power supply itself is less expensive than a CDW transformer. The cost of a CDW machine as compared to the FRT power supply depends on several things when you look at it as a total system. Obviously, it depends on how many heads you got to utilize, and also the machine construction. You also have to take into account the fast follow-up device you're using. So it's difficult to say that the FRT is always cheaper. It depends on the application, but from a power supply and transformer application, the FRT unit is more cost-effective.
Okay, thanks. All right, here's another one, Don. How sensitive is FRT to plant wiring / primary supply challenges, common in many industrial plants?
This is a very good question. You're going to have a turns ratio on these transformers around 37 to 1, which is a low turns ratio, which causes a high current pulse on the primary, obviously, back to the plant. Most of the welding plants that are set up for resistance welding can handle this type of load easily and have other systems in the plants that are taking anywhere from 1,000 to 3,000 amps on the primary. Yes, you have to also realize that this is a very short pulse width. So when the pulse hits the line, it's basically a 3 to 10 millisecond pulse. It's not a cycle or 2 cycles where it's going to really drag the primary equipment down like a typical resistance welding machine would. So you will see a very small hit on the primary, but it's for a very, very short period of time, so it's not nearly the same as conventional MFDC technology.
Okay, hey Don, can we follow up with another one right here? Here's one on how does this compare speed-wise to conventional resistance welding using an SCR?
It's a lot faster. First of all, referring to SCRs, that would be AC technology, and when you fire a CD machine, that's an AC transformer, but you're only firing in one direction using capacitors as a storage bank. If you're comparing that to standard AC with an SCR, it would be much slower. Generally speaking, these type of currents that we're showing here, it would take 2 or 3 cycles of time or 60 milliseconds in order to achieve those type of rise times.
Okay, thanks, Don. I got a couple people asking if this is going to also be available on demand, and yes, it will be available on demand. You'll receive an email with the information that will be located on the IEEE website. So you will see that email probably tomorrow. Donnie, how about this one? They're asking if you can elaborate on the importance of the fast follow-up when using this technology.
Yes, whatever form of fast follow-up you are utilizing for this is very important to the process in making a high-quality weld. Because we're dumping so much energy into the weld or the fastener at one time, any delay in that force follow-up will act as a lack of force, and you'll end up with a lot of expulsion from blowing out the material that you're trying to weld. So, yes, the fast follow-up device is extremely important, just as it is in capacitive discharge welding. Okay.
So, Don, here's one for you. Is the FRT power supply limited to a given amount of weld time?
No, that's the beauty of it. You can put a very quick pulse at the beginning of a standard weld schedule if you want.
Okay. Donnie, how about this one? How well would this work for a larger ring projection weld?
That's the type of application this technology is useful for. I mean, it can be applied just like a standard projection welding equipment could be, but you do have the availability of having the fast rise time to help with that weld, specifically on the advanced high strength materials, hot stamp boron, dual phase, that type of an application.
Okay. Speaking of fast follow-up, have you compared pneumatic versus servo?
The machines that the tests were run on were done with air over oil cylinders with a spring follow-up in them. It really doesn't matter whether you're using a servo to drive the head down or an air cylinder. What you have to have is fast follow-up incorporated into that, and generally that's a spring. There are some of the older machines that also have a diaphragm-type head, and diaphragm head also works exceptionally well. It's just a little bit older technology for fast follow-up.
Hey, Don, can you follow up with this one, too? Does the FRT solution offer any benefit to a seam welding application?
Only right at the initial start of current. The unit could be used for seam welding in a constant current mode. The current would go up much faster at the beginning of the weld.
Okay. What about current level you have reached? Donnie, can you answer that for us?
Well, you have the ability to put two of these units together. In that case, it actually cuts down on the impedance and actually drives the current, allows you to drive the current higher, faster. So really, it's based on the rectifier curve charts. Is kind of the limiting factor, and really the amount of current you have available from the weld timer. But yes, it's just like a standard MFDC unit. You can put these together and achieve even higher currents.
Okay.
I'm going to follow up on Donnie's answer. We have done a double unit in the south at a customer where we had 140,000 amps. You could have used a triple, but you need a real big weld control. So once again, it has to be related to the limit of the weld timer you have.
Okay. All right. We got a lot of questions coming in, so really appreciate this, guys. So bear with us here. Here's another one. Don, can you answer this? Are the FRT available for purchase right now? How many models / KVA ranges are available?
We have one specific unit right now, which is our TDC 7537, and that can be, as we just mentioned, put in a double or triple configuration mode. But we have one specific model. That relates to another question we got a little bit earlier, is what did we do to this transformer that's different? This transformer specifically was designed with a very low internal impedance. That included redesign of the primary coil arrangements, redesign of the rectifier for close coupling in order to drive down the internal impedance of the transformer. I won't get too much deeper than that, but it is a different transformer, and that's why it performs even better than most of the standard MFDC transformers out there.
Hey, Don, here's another follow-up for you. You mentioned the ability to weld copper with this technology. What sort of applications has this been applied to?
We've only had 3 or 4 applications where they were actually welding copper. They needed to have a very fast, high current pulse to weld some copper connectors onto wire and also to each other with a projection on them. And that was first proven with a design of experiment in a lab, and then they bought equipment with the fast rise time transformer for production.
Okay. Donnie, let's send one to you. What are the limitations for gun arms to make use of this, the max resistance? How do you make sure it is the same depending on how much material is in the secondary loop, such as different points on a body in white?
Well, most of the applications for something you're utilizing fast rise time technology for are typically in a machine. So the gun arms are either related to the cable or they're heavier duty. Basically, the less resistance you have in that arm, the better ability you have to reach that rise time, or to reach that current in a faster period than you would with a standard MFDC unit. Once again, it's MFDC, so the impact of anything inside that gun arm, that secondary loop, is minimal.
Okay, Don, on this one, they're asking how long was the current pulse on the example that we were talking about earlier?
The ones that were shown earlier were between 3 and 10 milliseconds, and that's the average pulse time for welding. As an example, the projection welding that we were talking about specifically for hot stamped steel. We've done some that were longer than that with very large ring projections for welding water heater, full ring projections, things like that, where the currents were as high as 150,000 amps and the weld time was out to 1.5 cycles. But most of this is less than 1 cycle.
Okay. Don, can you also answer this? The question is, you are talking about SCRs in MFDC. up to what frequency can SCR go for MFDC?
Maybe I confused someone with my answer earlier. SCRs are connected to AC transformers and typically limited to 60 hertz. All of what we're showing here is MFDC using IGBT controls.
Right. How do you physically change the transformer to make it fast rise? You talked about that a little bit already, Don.
Yeah, I answered that question earlier.
So how about this? Is this process new, Don? That's a good question.
It is from the standpoint of using MFDC to create currents less than a cycle. With a lot of the current MFDC transformers, most of them are smaller and they have been designed for the end of robot applications and have a fairly high internal resistance and reactance, which has limited their ability to produce very high, fast currents.
Okay. Donnie, one of the questions is, which is the frequency of this transformer? I think is, what is the frequency of this transformer?
Yeah, it's designed, the one we have right now is designed to operate at 1,000 hertz.
Okay, so here's a question too, as far as what type of benefit will this provide for spot welding?
If you're welding aluminum, it can also be very helpful because the faster rise time with aluminum, the better. Obviously, especially because of the conductivity of the aluminum and the thermal heat transfer of aluminum is so fast. So we've had people use it on guns for welding aluminum as well, where once again the fast rise time has an advantage, especially on thin materials where the weld times are incredibly short.
Donnie, how about this one? Is anyone else producing or manufacturing this type of equipment?
Not that we are aware of, not in this type of a package. I'm sure there's companies offering other high secondary voltage units, but not that we are aware of as far as in this type of a package and with this kind of internal design.
All right, Don, here's another one for you. For projection nut welding application, does the FRT technology change the hold times for best weld quality compared to traditional MFDC?
From the standpoint of hold time, it really doesn't make any difference. We're talking about putting the weld current into the nut and the projections faster. Once that's done, the amount of hold time, once again, sometimes there are specific materials and nuts that are hold sensitive, but in this case here, we really have not seen any changes in a typical hold time at the end of the weld sequence. It's just a much shorter current pulse. Once again, if you compare this to CD, they're both producing the same basic current pulse in somewhere between 3 and 10 milliseconds. And as an example, where an M6 nut may have been welded with 18,000 amps at 10 cycles in the past, which would be 200 milliseconds, they're welding M6 nuts with 35,000 amps, but for only 10 or 12 milliseconds. So it's just a much shorter weld time, much higher current pulse, and it creates a much more consistent weld process.
Donnie, here's one for you. Is there a limit to the amount of secondary welding current the FRT can provide? We answered that a little bit earlier, but can you maybe answer that again?
Yeah. Currently, the only limit is primary current that can be provided by the welding control, and of course the primary feed lines to the machine. Once again, you're going to have to take the rectifier into consideration and make sure you're not over on duty for a given secondary current. We've done a process with 2 of these in parallel, providing around 130,000, 140,000 amps. Once again, short weld times, and you got to base it off the duty cycle. So just got to make sure you're underneath the curve.
Yeah. Don, you can answer this one here, please. Would you recommend this process for a Class A mil-spec welding aluminum? Will it be more effective in eliminating void?
We have not done this on a Class A mil-spec application yet. To be honest, most of the Class A mil-spec welding has more to do with using a forge force during the welding process to eliminate voids in the weld. I don't know that this fast rise time would have any effect to improve a Class A weld for military spec welding. Once again, it might be material sensitive that you need fast current rise time, and it might help there. But up till this point, we have not applied it there yet.
Okay. Don, during the presentation, Don talked about the repurposing of our FRTs. What exactly do we mean by that?
Well, in many plants, machines are retooled and reused for different applications and projects. Since the FRT-MFDC Power supply is a standard H-frame size and has two usable voltages for the secondary, 13 volts and 17.5 volts, that unit can come out of a machine and go into a gun cradle that'll accept an H-frame, be tapped down to 13 volts if you needed to in order to get to a lower inverter size and be able to be used as a spot weld inside a spot welding gun as long as the gun can accept an H-frame. Same thing is using it for standard projection welding. It can be taken from one machine or reutilizing that same machine with the dual tap settings. It allows you to use 13 volts or 17.5 volts. So just a little bit more flexible and reusable in different applications.
Okay, we're getting close to the end of our live Q&A. We're going to take a couple more questions here. If you presented a question and we have not been able to answer it, we will follow up later with that. So, Don, here's another one for you, and then we'll wrap up one for Donnie as well. But, Don, how much current can a single unit provide?
The unit that you saw in our example here can provide secondary currents between 70 and 80,000 amps for weld times less than one cycle or less than 20 milliseconds. So you could produce a 10 millisecond pulse up to 80,000 amps. Once again, that's relative to the secondary impedance of the machine. Someone pointed out earlier, one of my friends from the Ohio State University and EWI, I won't name his name, but he'll know who I'm talking about out there, asked a very important question that, you know, CD equipment, generally the rise time is related to the secondary reactance of the machine, X sub L. This is also directly related to the X sub L of the machine, or the secondary reactance and resistance. Those calculations have to be done for this technology just like they do for a capacitive discharge machine. The difference is that when you use MFDC to create this short high current pulse, the controller is driving the transformer at 1,000 hertz. So that is why this is able to achieve even faster rise times than a CD machine. For a given voltage, the MFDC will actually produce a faster rise time than a CD machine because the CD machine has a larger X sub L based on the machine and the transformer that's inside of it. You saw the size of that CD transformer earlier. It's quite large.
Okay, we're actually going to wrap up with two questions. They're both going to be for Donnie. Donnie, first one, is there special maintenance required for an FRT system?
As long as we're comparing it to normal MFDC, your standard spot welding or projection welding, seam welding, no. It's basically the same as conventional MFDC technology. You're using typically the same type of a weld control, so there's nothing special there. CDW technology does require special maintenance and safety procedures for working on the capacitors. That's not applicable to our FRT-MFDC technology.
Okay. And we got time for one more question, and that is, can you give an example for the appliance manufacturing industry where this FRT technology would make sense?
One example would be areas where you want to leave no marking. Obviously, that's dependent on a lot on the electrode conditioning, but due to the fast rise time and the smaller heat affected area, it's good for leaving no mark, non-visible surfaces on welding thin metals. Another application we kind of touched on a little bit earlier is the ability for special full ring projections and watertight fittings. We've seen that application be very successful as well.
Okay, guys, we've gone past our 30-minute mark here. So, Don and Donnie, thank you so much for answering the questions. Don, thank you for the presentation. This does wrap up our Q&A at this time. Once again, on behalf of Roman Manufacturing, we'd like to thank you for your time and your participation today. If you have any additional questions, even past the webinar time frame here, please don't hesitate to contact us. You can reach us at marketing@romanmfg.com or visit Roman's website at www.romanmfg.com and send us a note through there. Thank you again for joining us today, and we look forward to hearing from you soon.